Okay, now we want to use the derivative to find the high and low points of a curve. Okay, these are called maximums. So this hiker's walking along this trail, and this curve is defining the shape of this trail. This would be a high point for that curve, and this would be a low point in here. Now there's other low points in here. You can have more than one low point. You're just looking for that low point, not necessarily the lowest point. So now when we want the highest or the lowest points, let's say f is a function defined on an interval I that contains the number c. F has an absolute maximum value. That means it will be the highest y value for all the numbers in that interval. So if we've got this interval I, so this I is just all the numbers inside of that interval. There's some number c in that interval that is going, if it's an absolute maximum at c, then that means that it has the largest y value for all the other x's that are inside of c. So it might be something like that. So at c, right here, is the highest point for all the other x's inside that interval. Likewise, f has an absolute minimum if you take every other number in that interval, every x that's in these intervals, is going to have a bigger y value than what it has at x equal to c. So at x equals c, then this would be the lowest one. So this would be an absolute minimum if it's the lowest, where the lowest y value actually occurs. So now let's look at 4 cases here. This first one, I'm looking at a function that's defined on the interval from minus infinity to infinity. I want to see if there's absolute maximums or absolute minimums. Now, you notice that this function, because the domain is minus infinity to infinity, it keeps going this way. It just keeps going forever that way. Likewise, it's going on forever that way. So there's never a highest point on this graph. So this function has no absolute maximum. Okay. Now, it does have an absolute minimum. It occurs right here. So the absolute minimum is actually 0. That's that y value, and it occurs when the x is equal to 0. Now, the next one, I'm looking on a closed interval from 0 to 2. So now I include the endpoints on that interval. So now the y values that this curve obtains on that interval go from here, which is the lowest y value, up to here where the highest y value occurs. Now there is an absolute maximum. Now the absolute maximum occurs here at y equal to 4. So the absolute maximum is 4. The maximum is that y value when the x is equal to 2. Now, is there a lowest point? Well, there is. The lowest point occurs down here at y equal to 0. So the absolute minimum is 0. That's the smallest y value on that interval. And that occurs when the x is equal to 0. Okay? So now this next example, I'm still looking at the function y equal to x squared. Now I'm looking on the interval from 0 to 2. I include the 2 but not the 0. So that means down here at the 0, that point is not included. There's a little circle down here, but then it has all these other points and it ends with the point there at x equal to 2. Now here it does have an absolute maximum. That absolute maximum will be the value of 4 here. So the absolute maximum is 4, and that occurs when x is equal to 2. Now, is there an absolute minimum? Is there a smallest y value? Well, 0 is not one of the y values. 0.1 is one of the y values, but there's one smaller than that. 0.01 is smaller than that. So you cannot give the smallest, because no matter what you pick, I can tell you something that's smaller than that, because it's everything right up until it gets to 0. So here in this problem, there's not going to be an absolute minimum, since there is no lowest y value that's attained there. Okay, and the next one, we're now looking at the interval from 0 to 2, and neither endpoints are included. So now we've got a circle down here at 0. We go all the way up to where we would be up here at the 0.24, and it's not included either. So if you're looking for the absolute maximum, there is no absolute maximum, because there is no y value that is actually reached on this function. 4 is almost reached. I can get as close to 4 as I want, 3.9, 3.99, but no matter what I say there, there's always something a little closer to 4. So there is no absolute maximum. in this graph, and there's no absolute minimum, since there's never a lowest y value that's actually the y for a certain point. Okay, now looking at these four cases, we had an open interval here that didn't have an absolute maximum, but it did have an absolute minimum. We had a closed interval, 0 to 2, that did have absolute maximums and minimums. We had an interval that was half open, half closed, which had the maximum but not the minimum. And here's one that's open that didn't have either. Okay, so it looks like right now the only one that had that absolute maximum minimum was the one that was on the closed interval. Okay, so we want to find out, when will we know that there's going to actually be a maximum and a minimum, an absolute maximum and minimum. Okay, so now here's a couple more examples. We suspected that it might need to be a closed interval for it to have a maximum minimum, but these are two examples where they're actually defined on a closed interval. See, it's defined from 0 to 1 here, including those endpoints, so that is a closed interval for the domain. But look at the endpoints. We do have an absolute minimum here. The absolute minimum is actually the value of 0, and it occurs when the x is 0. But there's no absolute maximum, because if you look at where the highest point would be, there is no point there. So we're getting as close to 1 as we can possibly get, but we never actually reach that highest number. So there's no absolute maximum. But this function is defined for all x's in between 0 and 1. It is a piecewise function, though, and that is probably why it's not going to have the absolute maximum there, since we have that discontinuity at that point. Now look at this other example. This is defined on the closed interval from A to B, because we do have y values at those endpoints. But in the middle of that, we do see a discontinuity here where it goes up, stops, takes a jump up, and then it comes on down. So there is no absolute maximum, because that highest point, which would be at this dot right here, is never actually a y value for a point. So there's no absolute maximum here. We do have an absolute minimum. It occurs over here. Okay, so these are two cases that shows you that being defined on a closed interval is not enough to be able to say that there is absolute maximum or absolute minimum. Now, one thing I want you to be aware of is the word extreme value is talking about an absolute maximum or an absolute minimum, or sometimes even local maximums and minimums, which we'll talk about in a little bit. But extreme can be high or lows of a graph. Okay, so what conditions will we need to just know for sure that there is going to be a minimum or maximum value on an interval? Okay, and those are given to us by the extreme value theorem. A function that's continuous on a closed interval has an absolute maximum and an absolute minimum. So this is how we will know for sure we do have absolute maximums and minimums. We have to have a closed interval, and the function has to be continuous on that interval. Okay, so now looking at this graph, I want to find the locations of the absolute maximum and absolute minimums on this value, on the interval from A to B. Well, I can see it is a closed interval. It is continuous on that closed interval, so I know there are going to be some. There are definitely going to be absolute maximum and minimums. So the extreme value theorem does satisfy the conditions. So it does hold here, and we know the absolute maximum is going to actually be here when the x is equal to the a. So that's where it occurs. That's not what it is. The absolute maximum is actually that y value, and then the absolute minimum does also occur, and it's going to occur at x equal to c. So the absolute minimum occurs at x equal to c. It'll be f of c, though, that y value. Okay, in this next example, we see a function that's not defined on a closed interval, because at the point x equal a, there is no point, and neither is there a point at x equal b. So this is not a closed interval. Okay, so f is not defined on a closed interval, and it's also not continuous. So we've got this little jump here in the middle. So there's a discontinuity there, so it's discontinuous, and it's not a closed interval. So there's no guarantee of absolute maximum or minimum. Okay, You can see in this graph there is actually an absolute maximum. It would occur right here. So there is an absolute maximum at x equal to c, but there is no absolute minimum. There's not one guaranteed by the extreme value there. Okay, so now the other type concept. We have absolute, the highest, the lowest, absolute minimum. Now we're talking about local maximums and minimums. Local means that if you have some interval for which it's defined, C has to be an interior point, so it can't be the end point of an interval. It has to be a point inside of the interval, so there has to be points on either side of it. And it will be a local maximum if that will be the biggest y value for all other x in some interval around it. So now it's not saying it's the very highest, but it's saying, like at this particular x equal to c, it's saying that if there's some interval around c where it would be the highest point, see in this interval I here that I just highlighted, at c it is the highest. So this means this is a local maximum. So it's a local maximum. The local maximum is actually f of c, the y value when the x is c. Okay, at this point D here, is there an interval around it for which it's the lowest y value? Well, there is. Just take some interval here and looking at that part of the curve, that is the lowest y value. So this would be a local minimum. Now the local minimum is actually is f of d, the function, the y value at x equal d, and it occurs at x equal d. Now, in this next one, at E, this point E over here, notice that it is also a high point, and there is an interval around it where it's the highest. You know, for just a little region around it, it is the highest. So that makes this a local maximum. But looking at the whole graph, it's also the absolute maximum. Now, you can only have one absolute maximum. You know, you might have it occur at more than one spot, but there's only ever one absolute maximum. You can have lots of local maximums, you know, just high points. So here's the local maximum, and here's a local maximum, as well as the absolute maximum. Now, this end point over here, that's a minimum point. So that is a minimum, but it's not a local minimum, and it's not an absolute minimum. It is one of the low points, but it's not an absolute. It's not absolute because there's other places where it's actually a lower y value. The absolute minimum is actually occurring over here at x equal to a. So this is the absolute minimum. Okay, and the absolute maximum occurred over here. And local minimums only occur in this picture here. Okay, you cannot have local minimums at the endpoints because of the definition. It has to be an interior point to be a local minimum or maximum. Okay, so looking at this picture, I want to find the local maximum and minima. Start at the beginning and let's find high and low points. Now here's a high point. It's not the absolute, and I know it's not a local maximum because it's not defined on a region around it. So it's got to be an interior point to be a local maximum. The second point that we get to, that low point, this one is it's actually a local minimum and an absolute minimum. Okay, this high point here, this would be an absolute maximum. It actually is the highest y value, and it's a local maximum. This point right here at x equal to r, we actually have a local minimum, but it's not the absolute minimum. Okay, and the next high point here, notice that looks like the y values are the same amount. That's why we actually have two places the absolute maximum occurs. Okay, you can't have two different heights, but the absolute maximum there is whatever that y value is. So f of s is the absolute maximum, or f of q. This is also a local maximum. This last one is a low point, but it's not a local minimum because it can occur at an endpoint. Okay, and it's also not an absolute minimum because there's a lower point over here at x equal p. Now, if we were looking at the derivatives of each of these, at the local extreme values, which would be at this point right here, now notice the way this curve kind of comes through. You've got this sharp point and then it kind of turns. There would be no derivative at this point. The derivative is not defined at those sharp turns like that. At this point, the derivative, so I'll just say f prime of q, is actually going to be 0. The slope of the tangent line there would be 0, since it's a horizontal line. At this local minimum, the tangent line would look like this. The slope of that tangent line is 0. So f prime of r is 0. At s, the tangent line at x equal to s is a horizontal line, and so that means that the slope of that tangent line at s is also going to be 0. And then the b, there's no local minimum or maximum there. Okay, so now one thing I want you to notice here, let's say f has a local maximum or minimum at a point C here. Now there's going to be two things. If that is the place where the local minimum or maximum occurs, there's something about the derivatives I want you to be aware of. Look at the secant lines passing through that point and a point to the left. So I'm going to look at another point x less than c. So if I looked at a point here and look at that secant line between those two, or look at another point here and look at the secant line going through those 2 points, or up here and look at the secant line. Notice all of these secant lines have a slope that's positive. So the slope of all the secant lines to the left of this local maximum are going to be positive. To the right of that local maximum, if I pick another point, let's say I pick a point here and take that tangent line or that secant line through those 2 points, or move the point up a little closer here and take that secant line through those, or here and take the secant line through that and where x is equal to c, all of these slopes of secant lines are negative. So slopes are positive to the left and negative on the right. Now this is going to be true if x equal to c here is a local maximum. That's how we're going to actually determine whether it's a local maximum or a local minimum, is by looking at the slopes on each side of that critical point and figuring out whether the slopes are positive to the left and then negative to the right. If they're positive to the left, that means they're rising like that. If they're negative to the right, they're coming down. So we'd have to have a local maximum up here. Had it been the other way, had the slopes been negative to the left and positive to the right, we're going to have a local minimum here. So that's what we're going to use to determine whether we have local maximums or local minimums. And then we'll have some of these points where those might occur at are called critical points, and I'll show you how to find those. So if f has a local maximum or minimum value at c and the derivative exists, okay, so this one had to be a situation where the derivative exists, then if that derivative does exist, that derivative must be 0. So that's what we're going to use to be able to find these critical points.